6.5 trapezoids and kites. Here's some quadrilaterals that you might see in your life in situations where you're flying a kite. This is called a kite. Okay, these two side lengths in green are the same length, and then in red, these longer side lengths are also the same length. Okay, and then here, this is what you call a keystone when you're building an arch. It's the keystone because it keeps these rectangles from falling all the way down. It wants to slide this way, kind of off to the side, and this one wants to slide off to the side this way. So this keystone keeps them from going where they want to. It's the wedge that holds it all together. And this is an example of a trapezoid. It's a quadrilateral where one set of sides are parallel, the other set of sides are not. Okay. This is more specifically, we're going to call this an isosceles trapezoid. So in a trapezoid, the two parallel sides, okay, these parallel sides are called the base, and the legs are the non-parallel sides. The base angles would be the two angles off of the base. Now these could be congruent, they might not be, but they're off the same base angles. So these two are not the base angles. Here's another set of base angles on the top, okay, because the base is not just on the bottom. Now, if the legs are congruent, we call it an isosceles trapezoid. If these two blue segments are congruent, it's isosceles. So there's kind of a key idea here that isosceles trapezoids have a vertical line of symmetry. Basically, you fold this in half. It's going to be symmetrical if it's isosceles. Not all trapezoids, just isosceles ones. So we have some theorems about the isosceles trapezoids. If a trapezoid is isosceles, then each pair of base angles are congruent. And then the converse to that is also true, that if a trapezoid has a pair of congruent base angles, then it is an isosceles trapezoid. So if it's an isosceles trapezoid, these sides are the same, then the angles, these angles are congruent, and these angles are congruent. And if one set of base angles is congruent, then these sides have to be congruent. And the last theorem is if and only if, so it works both ways, so no need for a converse. Trapezoid is isosceles if and only if its diagonals are congruent. So if these red lines are going to be congruent to each other. So here's our first example. We obviously have a quadrilateral here with four sides, and we know one set of sides is congruent to each other. We're assuming that this is going to be a trapezoid where this is parallel to this one, but these are not parallel. We can find out all the rest of the information. So we notice that it's an isosceles trapezoid, so our base angles have to be congruent. That has to be 45. And there's different ways to do this. These two angles have to be the same. And we know they all add up to 360. Or you can use the idea that these lines are parallel. These are consecutive interior angles. Consecutive interior angles have to add up to 180. If it makes sense, 180 plus 180 here gives you a total of 360. So that's what's going to make this thing work. So 135 plus 45 is 180. So that's a 135-degree angle in that one as well. Now we're going to show in a coordinate proof that trapezoid ABCD, or excuse me, quadrilateral ABCD is a trapezoid. So I'm going to plot the points. X is 5, Y is 0, X 0, Y 5, 4, 7, and 7, 4. Oops, put a 4. I wanted a D. Alright, so here's our quadrilateral A, B, C, D. Now, easiest way to show something as a trapezoid is first, is this a quadrilateral? Yes, it has 4 sides. And then I'm going to show that these two segments have the same slope. So I want to show BA is parallel to CD. And then I want to show that BC is not parallel to AD. So I want to show that exactly one set of sides are going to be parallel. So the slope of BA needs to equal the slope of CD, which is rise over run, up 3, backwards 3, so that's a rise of 3, negative 3, 3 over negative 3 is negative 1. And it's confirm, up 3, backwards 3, up 2, let's go up 5, backwards 5. So, right, my slope, so that's the same thing as negative 1. And then we'll show the slope of BC. And the slope of AD. So, slope of AD is up 4 over 2. 4 over 2 is the same thing as 2. This one's up 2 over 4. That's the slope of 1/2. And so we have one set of sides parallel, so it is a trapezoid. The mid-segment theorem for trapezoids. First, we got to understand what a mid-segment is. It's very similar to a for triangles. Okay, we find the midpoint. Remember, the midpoint divides it into two congruent pieces, and we connect them to midpoints. So the mid-segment of a trapezoid is parallel to each base, and its length is 1/2 the sum of the lengths of the bases. So this blue line is the length, half of the sum of these two segments. So how I see that is the average. It's the average length. And we'll see a couple examples to clear this up. Find x. So once again, this is a midpoint. It's been divided in half. And this is a midpoint, so this is my mid-segment. And this is x is going to be the average of these two segments. So I can add them up and divide by 2. So 11 plus 5 and divide by 2, I get 16 over 2, or 8. And over here, now this is not the mid-segment. One way you could do this is say y plus 8 divided by 2. That's going to equal my average of 10. So 8 and what number average out to 10? I need this to be 20 on the top. 20 divided by 2 is 10, so I need y to be 12. That's one way to do it. This is the kind of algebraic way. You could also look for a pattern that 8 plus 2 is 10, plus another 2 is 12. And then over here, 5 plus 3 gives you, plus another 3 gets you to 11. 5 plus 3 plus 3 is 11. So 5 plus 3 has to be 8. Kind of look for the pattern in the problem. And our last figure for today is a kite. We're talking about trapezoids and kites, and here's the kite, something that you guys might have flown as a kid. But a kite is the mathematical definition is a quadrilateral that has two pairs of consecutive congruent sides. So this side has to be congruent to that side, and this side congruent to this side. Okay, these are consecutive, but opposite sides are not congruent. This side cannot be congruent to that side. Okay, so if a quadrilateral is a kite, then its diagonals are perpendicular. The diagonals are going to be perpendicular here. And if you ever made a kite, you'd usually start with these diagonal pieces and then put the fabric on over the top. So if you have a quadrilateral whose diagonals are perpendicular, is that going to be a kite? And the answer is no, not necessarily. Remember your theorems about rhombus. A rhombus is going to have perpendicular diagonals, but a rhombus is not a kite. So the converse of this statement is not necessarily true. If a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. These angles will be congruent. These angles are not going to be congruent. So for a question like this, find the perimeter of this kite. You might look at this and say, we don't know any of the outside side lengths. Okay, you don't just add the lengths of the diagonals. You have to actually remember that this is a right angle and then use Pythagorean theorem. Right? 3 squared plus 3 squared equals a squared. Call this a. 9 plus 9, 18, square root of 18. This will be the same. We're using the same numbers, square root of 18. Remember, consecutive sides are congruent. This side over here will be 3 squared plus 5 squared, which equals, we'll call that c squared. 9 plus 25 is 34. So this is the square root of 34. And this has to be the same. So square root of 18, I'm adding two things that are the same. Add up all the sides. Here's a joke told by one of my students one time. So if you don't like it, it's not my joke. But here it is. What is the difference between a rhombus and a kite? A rhombus does not fly. Something to think about. No, there are other differences too. Hopefully you realize that the real mathematical difference is a kite and a kite, the opposite sides are not congruent, where in a rhombus, the opposite sides are congruent. That's really the only difference mathematically. So a lot of the theorems and formula for the area of a kite is the same for the formula for the area of a rhombus. You can use the same one, so they are very similar. There's the homework. If you got questions on anything I talked about, bring them up in class. Have a good night.